So in the last class we talked about RNN architecture, right? We talked how this works, and it is a very simple architecture if you think about it. It is just a simple basic tanh function and some basic addition and multiplications, right? So that is just adding some basic linearity and one tanh function, that is it. We understood how that can be used to understand a whole sequence, okay? Because it takes into account whatever has happened in the previous cells as well, and in each cell you will be feeding one by one each and every different token, right? So that was basically the whole thing about RNN architecture. So let us talk about the next architecture, which is LSTMs. So LSTM stands for long short term memory. So this is what LSTM stands for. But before we understand this, let us understand why RNN was a fail, or why, in which ways RNN could not help. Okay, so RNN cons. So let us talk about that. So the very first of all, let us talk about the pro as well. Okay, so one of the biggest things about RNN is basically it helped us understand how to solve sequence problems, right? So whenever you have any sequence related problems, always remember that what you are going to work about or work on is basically different sequence models, right? So or models that can take into account whatever has happened previously, right? So what is the con? See, even though it could understand this whole thing, the problem was RNN still had very short span. So it got, if you give it a paragraph, it won't be able to understand each and everything from the paragraph, right? It will only be able to understand a part of it, because it cannot understand the whole thing, because it does not give attention, or it does not understand such big sequences, okay? So that was one of the cons of RNNs, because it could not, even though it understood the state of the previous cell or the state of the previous token or word, in this case previous sequence, okay, it still could not understand the whole context as together, right? Because think about it, you had these RNN cells, right? And all of these, they were passing out hidden states, and these hidden states were actually part of this old previous cell, right? So it was somehow, it gave more value about the previous cell than it gave about the entire context, right? So that was one of the problems with RNN. Hence we have LSTMs. LSTM stand for long short term memory, okay? So that is what LSTM stands for. This is a basic architecture of LSTM, okay? So there are a lot of things, don't worry, we will cover them one by one, so you will be able to understand slowly what is happening in LSTMs, okay? So this is the whole architecture. There are three, in LSTMs you have three gates. So there is an input gate, a forget gate, and an output gate. So the one thing that makes LSTMs better than RNN is basically it understands the entire global context of the particular sequence, alright? Because there are two things here in mind that they have taken into consideration, right? So one is the cell state. So the cell state basically gives you the global state, okay? So let's suppose you have an entire sentence, right? So in that sentence, it will be able to understand the global context or the global meaning of the sentence, of each word in that particular sentence, in that format. So this one here, this is able to understand the cell state, and then you also have the hidden state. So hidden state is basically used to understand what was happening in the previous cell, okay? So it takes into account these two things, hence it is able to understand what is happening in the relation or in the neighborhood of everything. At the same time, it is able to understand what the global context is, or how this word is related to the global context of the entire thing. Hence LSTMs were a hit, and they gave better performance as in they were able to understand longer sentences, okay? So that was one of the things that made LSTMs very popular, and they are still very popular at the moment. So what we are going to do is basically, now we are going to break down this entire cell structure into different parts, so that we can understand each and everything. So this is basically, see, this here, this is the very first step here. This is the very first step here. If you look here, right? So this here, this is your cell state, okay? So this gives you a global idea of the entire input that you are giving, entire sequence that you are giving, okay? So this is more of a conveyor belt, because you don't have or you don't make a lot of changes here. What you do is basically you make changes in the previous hidden cells, and in that way you just concatenate that to your cell state. Okay, so you can see here there is not a lot. You have one multiplicative here, one multiplicative. These are dot multiplications, by the way. Okay, so these are dot multiplications and one multiplicative value, and then there is a summation. We'll talk about each and everything, but yeah, to give an idea, this is basically your global cell state, and this keeps into record everything. So the next thing is basically this. Let us talk about our very first gate, which is the forget gate. So this is our forget gate here. This here represents your forget gate. So here what happens, if you see, so you have the input ht minus 1. ht minus 1 is basically, see, xt stands for x or input at time step t. Alright, ht minus 1 is previous cell's hidden state. Okay, so this gives you the hidden state of the previous cell, and xt is basically your input at time step t. Okay, so they are passed through a sigmoid. So first you will get obviously multiplied with weights. That happens, add of bias and everything, so that remains the same thing. So you will have weight multiplied with x, add a bias, and in the same way you will have the same thing for the hidden state. So you will have a weight. So these weights are going to be different, by the way. Weights and biases are going to be different. And what you can do is basically, see, you might be thinking why I have written two different bias terms, right? Here you have only one bias term. See, bias terms are basically constant, so you either write one of them or you add both of them and write one together. It means the same thing, right? So now you have the weights that will be multiplied with here. So this is basically the same as, if you remember, even in MLP we talked about it. Here you had the summation function, and this was followed by an activation function, right? So in the same way, the same thing is happening here. Here is the summation function, you multiply it with the weights, add the bias to it, and this is passed through a sigmoid function. So sigmoid is my activation. So if you remember sigmoid, if you remember the graph and everything, sigmoid lies between 0 to 1, right? So if you think about it, this is in this way. Forget get here stands for the maximum value it can give is either 1 and the minimum it can give is 0. Okay, so if it gives a 0 value, so that means this is not a very important input and hidden state. So let's say we have a big sentence, okay, and in that sentence we have is or and stuff like that. Okay, so these words are not that important. So here your values will come very close to 0. Okay, so 0 means basically you have to forget this, hence the name forget gate. And if you get 1, some value, let's say it gives you some location of a place or some name or something like that. So let's say it gives you the thing Greece. So you know Greece is a place. So what will happen, it understands, okay, this is an important word. So in that case your values will be close to 1. So depending upon the whole context, this is basically your forget gate. Forget gate, basically this decides how important your input or your previous hidden state is, right? So that you can then decide how much of it you want to add to the general context of it. See, after getting the value, if you remember here, you had this value, right? You got this value here. This will be multiplied with the cell state. So cell state is a global state. So this basically helps you decide how much of this is important. So if it is very important, it will add more value to the cell state. If it is not important, it will add less value here. Okay, so this is all about your first gate, that is the forget gate. Next we are going to talk about the next gate, which is your input gate. So here also, so the thing is, the first part is very similar. Okay, so in input gate you have two parts, two different functions, and the reason for these functions are also there. We'll discuss about that also. But you have two different functions. Okay, you have a sigmoid function, you have a tanh function. So you have the input ht minus 1, which is the previous cell hidden state, and xt. xt is your input in this particular time step. Okay, so this is going to pass through a sigmoid function, right? So you have the sigmoid function, This will be multiplied with the weights. You have a bias added to it. This will be passing through the sigmoid function. This is the same thing. It will give you values between 0 and 1. Okay, so this basically tells you how much of the previous state value or the present current current input you need to forget or remember. All right, so that is what this gives you. Next, what happens is these things will also pass through a tan h function. So tan h basically if you remember that the values lie between -1 to +1 in tan h. Alright, so what happens when you apply a tan h is basically it gives you the relation that this word has with the entire global context state. So let us suppose you have a word or you have something that totally contradicts the entire cell state. Okay, so there is something and it totally contradicts it. In that case your values will be close to -1 because this totally contradicts, so it does not match the whole thing, it gives a negative relation. So yeah, the whole point of this was, I forgot the term, the whole point of this tan h is basically it gives you the relation of this particular word or the previous hidden state with the entire global context. Okay, so that is why tan h is used. The value lies between -1 and +1. Okay, so what happened here, if you think about it, you had two activation functions, one sigmoid where you have the weights, the weights will be multiplied with the hidden state and x, that is your input, and a bias will be added, and then you also have a tan h function. So tan h function, what this will do is basically the weights will get multiplied, the bias will be added and will be passed through a tan h function. So tan h function will basically give you the relation that the particular term or the particular input has with the entire global context. Alright, so this is basically your input gate. And now here what is happening, this will basically show you how your cell state will change. So if you see about here, if you see here, cell state totally depends on your forget gate and input gate. It has no relation with your output gate, we'll see that. So it totally depends on your forget gate and input gate. So the forget gate will, this multiplication basically means dot multiplication or point multiplication. So what that means is each and every term will be multiplied, and in this case what will happen is, see this, so it depends on your input, your forget gate and your input gate. So your forget gate value will now be multiplied with the cell state, which gives you the global context, and that will be again added with the multiplication of the value that you got from the tan h and sigmoid. Okay, and that will be added to your cell state, because this will now give you the global relation or the way in which this particular word is related in a global context. Okay, so that is why this will be added, and here forget gate will basically give you how important this particular input is. Okay, so that multiplication will give you, okay, this is this important, this is not that important. So now your global context will change accordingly, right? So this was your previous global context, this is now your next new global context for this particular cell value. Okay, then here you have your final part, which is your output gate. So this is your output gate. Here things are very simple, nothing much is happening. Okay, so the whole point is you have already gotten your input gate and your forget gate, you have all the values, you have updated the cell state. Now what you have to do is basically you have to get two values. One will be your output y. So every cell will give you the output y, so it is up to you whether you want to use that value or not. If you remember, we talked about different types of architectures. Some architectures, what happens was you have a lot of inputs but you have just one output in the final, right? So those structures were many to one architectures. So in that case what was happening was all these cells, they always give out some value, but we will be discarding it only and we will be using the final cell output. Okay, so that is the only thing that we will be using, and that will give you basically the value. Okay, so you get value regardless, so it is up to you whether you want to use it or not. Okay, that is the whole point of this. And then finally you have the output. So in output what is happening is, this is again a sigmoid function, so it is passing through a sigmoid function. Here though, after having the sigmoid thing, you first multiply with the weights, add the bias, you have the sigmoid, you get the activation, then you have ht. So ht is basically your hidden state. So my hidden state for this particular cell is basically what? This output ot that you got, that is from the sigmoid, multiplied with tan h of ct. Ct is basically a global cell state. So these two get multiplied and you get your HT. Now if HT is passed through a softmax layer, this gives you my YT. Here you will get your YT output if it is passed through a softmax layer. Okay, so depending on the context you have to decide what type of layer will be using, but yeah, so that is the whole point of how you will be getting this whole YT also. So this is basically everything that you need to know about LSTMs. If you are interested in this concept more and want to learn more, what I will suggest is visit this website here. Okay, this blog, it is very well written, and here you can go, and this is written in 2015 by the way, but even then it is very relevant because they have provided so many things, so many architecture, so many images, it becomes very easy to understand. Okay, so I would suggest if you are interested in learning more about LSTMs, go here, read more about it, and yeah, definitely understand and practice this architecture because this is very important. This is used in a lot of cases. So once again, let us go back and revise one more time very quickly what is happening. All right. So it starts, the whole LSTM starts with 3 different gates, and the reason why we use LSTMs is because we need to understand about how a particular sentence or how it behaves, a particular word behaves on a global context as well as on the context of each and every word. So we were able to understand using RNNs, we were able to understand how it behaves for a particular word, how it is related to the previous word, right, or maybe 2 previous words, but RNNs cannot understand the whole context or very big structures or architectures. Hence what we did with LSTMs was we took into consideration 2 different things. One, how it impacts the whole global context of the particular input, the particular sequence, and the second thing is how it will impact or how it will change what the problems are with the neighbors of the thing. Okay, so the neighbors of the sequence, the neighbors of the input. So it took these 2 into accounts to find out how it impacts the changes in the neighbors. What it did was it used hidden state, and to understand the global context it used cell state. Okay, so these 2 words are very important. I am repeating it many times so that you understand the whole thing. So in 3 gates, what are the 3 gates? You have the input gate, you have forget gate, and finally you have your output gate. So the whole point of this is basically you start with your forget gate. In forget gate what happens? Let's go back here. So in forget gate what happens? It passes through a sigmoid function. Sigmoid values lie between 0 to 1. So this tells you basically how much you want to remember or how much you want to forget of the input. Okay, and then what happens? It passes through an input gate. In input gate what happens? It gives you the relation with how the particular word or the previous hidden state is related in the entire global context. Is it a positive relation or a negative relation, and so on. Okay, and then finally you have the output gate. So output gate basically what it does, it gives you the hidden state value, and using these you can update your cell state. So that is all. Go through the equations properly. You will get asked a lot of questions from here, so understand it, learn it, and if you have any problems, again go through the blog. You will have the blog link given to you, and I hope you understand the video. In the next class what we will do is basically we will talk one more variant of RNNs. Okay, so we talked about RNNs, now we talked about LSTM. Next we will be talking about GRU. Okay, so this basically stands for gated recurrent unit, and we will talk about this and we'll understand the differences between each of these. And for now I hope you understand the video and keep learning.